we're doing today is looking at nitrous oxide emissions from these forage sorghum and switchgrass plots. Nitrous oxide is a greenhouse gas. Most oftentimes we think about CO2 emissions in the atmosphere as far as greenhouse gas and climate change and these things, but nitrous oxide is the second most potent human emitted greenhouse gas, along with methane as a third one, and its primary source is agricultural production of crops, and specifically nitrogen applications to soil. So we fertilize our crops to increase productivity, but that also results in nitrous oxide emissions. Same thing for biofuel. We must fertilize them to create protein to allow for biomass production, but at the same time we're releasing nitrous oxide. And so what we want to know is, how does that influence the net greenhouse gas emissions of this production system? All of these will end up significantly reducing greenhouse gases emitted in the atmosphere compared to, say, the combustion of fossil fuel, but their relative emissions will be significantly influenced by nitrous oxide. And so what we're looking at is a in-rate versus nitrous emission for both of these crops to see which one can produce the most biomass or the most ethanol per unit of nitrous emitted. So what we have out here are these small chambers, and they're made of essentially two components. We have the anchor, which is pushed into the ground, and we try to leave that in the ground throughout the year. In the switchgrass plots, in fact, we've not taken them out for 2 years. In the sorghum plots, we have to take them out only when they plant. And so that's a frame that's pushed down into the ground, and it's got a little trough that we fill with water. And then we have the lid, and so they put that on the anchor, and then they immediately take a gas sample. And then every 15 minutes after that, for 45 minutes, they take a gas sample. And what that allows us to do is look at the relationship between time and concentration, and we can calculate a flux. When we get that flux, which is a rate of transfer of a molecule from the surface of a specific area per unit time, then we can extrapolate over time, in this instance over years, with all these individual point data sources, aka once per week. We can extrapolate that across time and get a cumulative average emissions to say this plot has released so many pounds or kilograms of nitrous oxide over the past 3 years, because that's really what we want to know. And then that data, as we move forward, we'll actually use that data to calibrate some models.